Okay. Hi, class. We are trying this snow day kind of recording happening. So I made this like notes thing to write on for us. I'm gonna have my camera off just because I'm looking at my notes a lot, and so I'm not even really looking at the camera while writing. Um, so sorry about that. So last week we were looking at the mean. So that was the sum of all values divided by the total number of values. Oh God, this is very laggy, but we're doing the best we can. Okay. Sorry, I might be talking very slow just because writing, I have to write so slow or it messes up. Okay. So let's say we had some grocery store prices for a protein bar. So this is an example. Costs at 8 grocery stores. Okay. And they are, everything's going to start with the dollar. I'm just only going to write it once. 109, 1.29, 1.35, 1.39, 1.49, 1.59, and 1.79. Okay. So these are all the costs. We see there are 1, 2, 3, 4, 5, 6, 7 costs. Okay. So to find the mean here, what we would do is we would add all of these costs together and then, oh, I'm so sorry. I forgot. There's a second one. Eraser. Yeah. That's not eraser. There we go. There's a value, a very important value I forgot, and that will mess up doing the mean if I don't have it. Okay. So we also have the value of 1 comma or 1.29. It's repeated. We have two. That's why I missed it. So we have two grocery stores that have it at $1.29. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8 values. There we go. That matches up with what I have in the notes. All right, so if we were to add all of the values together, we would end up with my calculator. That's not done in the notes. So we'd have 1.09 plus 1.29 plus 1.29 plus 1.35 plus 1.39 plus 1.49 plus 1.59 plus 1.79. That's going to give us 11.28. And then we're going to divide that by 8. And it'll give us 1.41. Okay. So this is our mean cost. I guess I'll add the dollar sign back in kind of right here, a little small. So it's $1.41, and that will be the mean or the average cost of this protein bar across these 8 different grocery stores. Okay. So let's keep going a little bit. Okay. So we don't always have to just find the mean. Sometimes they'll ask other questions of us involving the mean. So maybe they'll ask us to find the value of x such that the data set has a mean of 85. Okay. With our list of our data set being 90, 70, 100, 85, and X. Okay. So we know that our mean is going to be 85. And then we know that the equation of our mean will be adding all these together. So 90 plus 70 plus 100 plus 85 plus X all over. And then there is 1, 2, 3, 4, 5 values that we're looking at, including X, and we have to include X in order to solve for it. So that means we're going to be dividing everything by 5. So we want to solve for X here. So to do that, what we're going to do is we're going to add up everything and then we're going to solve. So actually what I want to do first is I'm going to multiply both sides by 5. Like this. Let's give myself some more room. Okay. So if we have 85 times 5, and then adding up all these numbers up top, you'll get 345 plus X all over 5 times 5. So this times 5 is kind of happening kind of on the outside if I put big parentheses here. And then what's happening is we're going to get this 5 canceling and this 5 canceling. See, this is in the denominator and this is in like the numerator. So we're allowed to cancel. It's multiplication, which is why cancellation from the numerator and denominator works. So then we're going to end up with 425 equaling 345 plus X. And that 425 came from 85 times 5. All right. And then when we subtract 345 from both sides, we end up with, I'm just running out of room a little bit, we're going to get 80 equals X. So that's going to be the value we would have needed in order to make the mean of this list be 85. Okay. So normally where I'd ask if there are any questions, but since we are not in a class, let's just do another example. Let's bring this down some more. Should let me start pulling now. Not enough now. If I pull it down. There we go. Okay, so let's look at another example. Okay, so the mean score on a set of 20 tests is 70. Suppose 2 more students take the test and score 95 and 100. What is the new mean? I know everything's kind of blending a little bit. Oh, question mark. Okay. So when we're talking about mean, another way to think of it is not just the average, it's so the mean is the value for which if we add it together n times and divide by n, we get itself back. Okay, so what that really means is if we have like score A, B, and C, with mean, well, in this case, let's just say this is three things, 70. That means the total A plus B plus C is the same as 70 plus 70 plus 70, which would end up being 210. It doesn't mean that A, B, and C all have to be 70. It could be 60, 85, 65. I think that works out. Or 60, 80, 70, something like that, where they're a little bit different, but if they all add up to be 210, we get the same thing. So when we're doing this test, when we have 20 tests that average to 70, what we can do is we can treat it as though we have 20 scores of exactly 70. So working with that, what we're going to do is we're going to pretend like we have 20 scores that are 70 plus our two new scores. That's the same as writing 70 plus all the way to 70 20 times. It's the same thing as 20 times 70. And then plus our 95 plus our 100. Okay. So for 20 of the scores, we have 70s, and then we get two more scores. So we're going to have 22 total scores now. Okay. So when we do this and we add them up and we divide them, I'm going to imagine you have your calculators in front of you. We're going to end up with a 72.5 mean. Okay. So with that, again, I want to ask if there's any questions, but there's no one here to ask questions. So, what we're going to do is I'm going to write out a question, and I want you guys to like pause the video, attempt it yourself, and kind of like I would normally do in class, and then we'll work it together. We're going to see how this goes. All right. So 3 cars are driving on a racetrack. Driving on a track. The mean speed of the 3 my handwriting. This is not great. Of the 3 is 100 miles per hour. Okay. So car X drives 109 miles per hour. Car Y drives 100 and, whoops, no, 114 miles per hour. Find car Z's speed. Okay. So I'm going to let you guys pause for a second to think about this, see if you can determine it yourselves. Okay. Hopefully you've paused it, you've come back, so let's work it together. So first, we see that these two scores, 109 and 114, are both bigger than 100, which is our mean. So what that means is that car Z's speed has to be smaller than 100. Because if it was bigger than 100, we would never like get to 100. Since it's the average, one of our values has to fall between it. So to figure it out, we're going to do 109 plus 114 plus, I'm going to use a Z since we're looking for car Z's score, divided by 3. equals 100. If I multiply both sides by 3, which let me to give us more room. There we go. So if I multiply both sides by 3, I get 109 plus 114 plus z all over 3 times 3 equals 3 times 100. The 3's are going to cancel out. And then 109 plus 114, that's going to give me 223 plus z equals 300. All right, and then I'm going to subtract that 223 on both sides. And we're going to get, if I kind of do this, we get 770. So we're going to get x equals 70, or sorry, we're using z. It's old habits, they die hard. All right, so we're going to get z equals 77. Oops, that was a bad box. Let's try that again. It's a little better. Miles per hour. The little writing tab I'm using, like I can't look at it while I'm drawing on the whiteboard thing. It's a kind of confusing system, so I'm sorry if the handwriting is not as good as normal. Okay, so now that we've done a lot of problems that have to do with speed and mean, let's talk about the other two centers of data. Draw a line here. Oh, that was bad. Let's try that one more time. That was a little better. Okay. So the median is the middle value. Oops. In the sorted data set. So we're thinking a median, when we're driving, the median is the like center of a freeway. So this is going to be like, or halfway point. The two middle values. If the number of values is even. Okay, so what that'll look like, so let's look at an example here. I'm going to already give us our data set ordered. So let's have 2, 4, 6, 9, and 33. All right, so if we want to find the median, that's going to be the middle value. So I kind of imagine I go in the middle and I cut it right in half. If I fold it, and right here, this 6 value, this is my halfway point. So that means my median, which I'm going to just abbreviate as med or mid, is going to be 6. All right. Versus, so that's when I have an odd number. I have 2 on either side. My middle odd number is going to be the median. And so another example, if we have an even number, let's say I have 3, 3, 5, 7, 9, and 33 again. So for this one, I have 3 on the left, 3 on the right. So I need to find the halfway point here between 5 and 7. And what do you know? The median point between 5 and 7 is going to be 6. So to find that, you do 5 plus 7 and you divide it by 2. 5 plus 7 is 12 divided by 2, which is how I got that 6. Okay. So that's one way. It's just truly the middle of our data. And I'm going to pause for a second because my dog is asking to be let out. So I'll be right back. Okay, back everyone. So that was our nice example of the median. So let's look at the other center of data, which we call the mode. So, whoops, that's not the right color I wanted. There we go. Okay. So the mode is the most common value. Or group of values in a distribution. Oops, distribution isn't. You've seen that enough? Okay, so for an example here, let's say I have the data 2, 4, 4, 6, 7, 13. So looking at my data here, my 2 appears once, my 4s appear twice, my 6, 7, and 13 all appear once. So that means that my mode would be 4, because everything else appears once. Okay, versus if we wanted to have groups, if I had 2, 2, 2, 3, 8, 9, 9, 9, 33, 33, something like this for my data. And this is nice and ordered. I'm giving it to you ordered. Sometimes my lab math will be mean and it'll jumble things up. So I'd recommend always writing things out in order on your scratch work and then going from there. It's just very helpful. All right. So there's 3 of these. There's 3 of these. 3 and 8, there's just 1 of them. And then there's 2 here. So since there's 2, that's less than the 3. We only care about the 3 values. So in this one, my modes, I'm going to have 2 because there's the even number of both of them are going to be 2 and 9. Okay. So those are nice basic examples, but we might have some more interesting ones. Okay. So again, a lot of the times they're going to give you data that is not ordered. So let's look at a more complicated example. So let's find the median. All right. So if my data is given as follows, 6.72, 3.46, 3.60, 6.44, and 26.70. All right, so I have 5 values and they are unsorted. So we want to put them in the correct order. So I'm going to order from smallest to biggest. So my smallest value here is the 3.46. The next is 3.60. All right. So that's this one taken care of. Let's kind of cross them off as we go. That's this one taken care of. So then looking at my remaining 3 values, my next one's the 6.44. And then 6.72. And 26.70 as my last one. That was crossing off this one, then this one, and then this one to get them nice and ordered. And then I want to find the middle value. That's going to be this guy here. He's right in the middle. And since we had an odd number of data points, that's expected that we just have a single value. Okay, so that means my mode, or sorry, my median is going to be 6.44. I'll just circle it. There we go. Okay. So now we're going to do a similar example, but we're going to be looking at an even number. And again, just practicing finding that exact middle. So example, we want to find the median. All right. So my data will be 6.72, 3.46, 3.60, and 6.44. So our first step is we always want to order our data. My smallest one is 3.46. Then it's 3.60. Then it's 6.44. And then lastly, it's 6.72. So all my numbers just rearranged from smallest to biggest. And then looking here, my middle point, I have 2 on the left, 2 on the right. So I'm going to have to find the middle. Middle, there we go. 3.60 and 6.44. So again, the way you do that, you take the 2 values and you add them together. And then you divide them all by 2. When you do that, you're going to get 5.02 as our median. Okay. So I'm going to write down 3 data points and I want us to figure out what the mode is for each one. So once I've written down the data points, I am going to have you guys pause the video, figure out the mode, and then we'll come back to it all together. All right. Find the modes. So for data set A, we have 5, 5, 5, 3, 1, 5, 1, 4, 3, 5. For data set B, I have 1, 2, 2, 2, 3, 4, 5, 6, 6, 6, 7, 9. And for data set C, I have 1, 2, 3, 6, 7, 9, and 10. All right. So I guess 10 is the only one that's 2-digit. So I'm going to kind of bracket it just so you know. Everything else is single digit. I just didn't put commas because I'm lazy. So pause the video, try to figure out the mode for yourself. Okay, let's find the modes. So here we have, can I just highlight? Oh, excellent. We have a 5, a 5, a 5, a 5, and a 5. Everything else, like there's 2 3s, but we can definitely see that there's a lot of 5s. Oh, and there's 2 1s. But there's 1, 2, 3, 4, 5 5s. So because there's 5 of them, that means our mode here will be 5. Okay. Then looking at the next one, we have 3 sets of 2s and we have 3 sets of 6s. Everything else appears just once. So that means is we're going to have 2 modes. So when you have 2 modes, it's called, whoops, it's called bimodal. Bi being 2, and it's 2 and 6. Whoops, that 6 looks bad. Let's try that again. There we go. All right. And then here on data set C, everything appears just once. We have 1, 2, 3, 6, 7, 9, 10. Nothing repeats. So when you have nothing repeating, we're going to have no mode. So if everything appears the same number of times, we're not going to have 7, I think there's 7 numbers here. We're not going to have 7 of them as our modes. There's just going to be none. It has to, like here, the difference is there's a lot of 2s and a lot of 6s and not a lot of everything else. So that's the kind of difference there. Okay. So something that's we want to watch out for when we're talking about mean, mode, and median is so the first thing is there we go. There we go. So mean and median only work with numerical data. E is being said. Numerical data. There we go. Okay. So that means not categorical. Because there's like an ordering to it. We need to be able to add and divide with the mean. And with the median, we have to be able to order our data in order to find the middle point. Okay, but the mode works with both. So the mode right now is the only thing we have that can work with categorical data. Because let's say you're talking about a bunch of students in a class and we tell you what sports they all play. You could have like 6 soccer players and then everyone else play like basketball, baseball, football, whatever other sports. There's no way to order the types of sports to find the median or add, subtract them, but you could say, oh, those 6 soccer players, that's the mode. So the most like common one there would probably be soccer. Okay. Oh, hello. Sorry, my dog is trying to get attention. Give me 1 second. Hi, BB. If I had my, you know what? Maybe I can turn my camera on just for a second to show you guys my dog. Hello, this is me. And that's my dog. That's Charlie. All right. I hope that actually showed while I'm scrolling my screen. Wait, I have an idea. I'll turn it off for just a second. And I go back to screen 2. Okay. Okay, I think that's this again. And that's my dog. Say hello to Charlie. All right. It's the one benefit of working from home is I get to show people my dog. All right, so I'll turn the camera back off and I'll go back to sharing my correct whiteboard screen. Here we go. All right. So that's the categorical data. And then, so we have one other type of thing to talk about. Not one other, I mean, we have several things, but another new type for us is going to be an outlier. So an outlier is a data value that is much more, or yeah, much higher or lower than the rest of the data. Okay. So, for example, if we look at salaries at a company, I don't know if salaries has 2 L's or not. That doesn't look right. I think it's just one. All right. So let's say we have a salary of 25,000, 25,000, 25,000. Maybe spice it up and throw in a 27,000. And then another one that is 2,575,000. Then I have that third zero in there. Okay. Obviously, One of these, that's not a one, that's part of the dollar sign there. All right, one of these is unlike the others. This is really large. If I have to take the average or the mean, I'm gonna kind of just approximate it. We'd end up with about like 5,500, or sorry, $550,000 as the salary. But obviously, most of the people at the company are not making anywhere near the 2 million. So what would be better would probably be the median or the mode would better represent. Okay. So that's something that can be careful is if you're looking at things and one value is really, really extreme compared to the others, the mean is not going to work as well. So that's going to be a downfall of the mean. Okay. So when should we use which category? Because we just saw something that can be the downfall of the mean. So it's best to use the mean when the distribution, when the distribution is symmetrical and there's no clear outliers. If you continue on with statistics classes, there's a formula, I believe, to find when something is like statistically an outlier. We're not going to deal with that too much for now. We're just going to use kind of common sense looking at things. And then it's best to use the median when the distribution is skewed. U is skewed, i.e. clear outliers. That should be a C. So we're going to kind of get to this later. We want to use the mean when our distribution, if we kind of arrange it, will kind of look like a bell curve. And we want to use the median when we have something that's maybe a little bit more skewed like this, where we have like a tail on one side. We will view these kind of graphs a lot more. So one of them is more symmetrical. One of them is less symmetrical, but you can still find most of the data points lying around the median. Okay. And so then the last one is we want to use the mode can be applied to both. So mode is only available. It's the only option with categorical data, which I'm going to abbreviate as categorical as CAT data. Okay. So for these next problems, they're word problems, so I think it's going to be easier to share my screen with the PowerPoint we're working with. Okay. So here's measures of center of appropriate to data type. I hope this is the correct one that we're seeing. I would just hope it's working. Okay. So for each data set given, we want to determine whether the data is categorical or numerical and determine the appropriate measures of the center for each data set. So the first one is the household income for a random sample of people in a state. So since we're talking about income, that is going to be money. So that's going to be numerical. because we can describe it using money and we can like add, subtract, divide, kind of do things with those values. And it has some meaning. And so for this one, since we have a random sample of people in a state, that our data should be pretty symmetrical. So for this one, we're probably going to want to use the mean. So for that, I can't, when I'm sharing this, I can't write on it. Sorry. So we're just going to have to say numerical, and the center is the mean, versus for section 2, the favorite fruit juice for a random sample of students in a school system. That data is going to be categorical. We can't add, subtract, divide fruit juice. We also can't order that in any sort of way to find the median. So for this one, it's going to be the data is categorical. So that means, oh, sorry, for this first one, the appropriate measures, we could have picked 2, so it probably would have been the mean or the median. For this one, we can only apply the mode. So that's because it's categorical. All right, so same thing here. Landline phone numbers for a random sample of people in the town. So while you might say, oh, this is numbers, you might think numerical, this one's actually going to be categorical. Because if we add 2 landline numbers together and then divide it, that's not giving you a new phone number. That's just giving you a random grouping of numbers. The numbers have they are actually important. So this is going to be, the data here is categorical, and the center for this is going to have to be modal, although there doesn't really, 2 people shouldn't have the same number, so it's probably going to have no center of data. All right. And then the height of a random sample of women in our Math 1313 class, so that's our QR class, that data is going to be numerical. And the appropriate measure for the center of that could be, it could be the mean, it could be the median, it could even be the mode. So that's could be any of them. And then lastly, for the daily snowfall in Boston in January. So it's talking about the inches or feet of snowfall. So that is going to be a numerical type versus if it had just said, yeah, so it's going to be the amount of snow that fell in that month of January in that one city. So that's numerical data, and appropriate measures for the center is going to be average, mean, mean, median, or mode. Okay. So that's going to be kind of it for those couple of examples. So let's go back to sharing with this screen up here. So we can go back to writing. Okay. So now let's talk about these actual kind of pictures that have to go with characterizing distributions. So characterizing, come on, work with me, data. My pen is getting laggier as the video goes on, which is really annoying. Okay, so we're going to have some shapes to our data that we want to talk about. So with that, we're going to talk about symmetry first. Okay. So a distribution, which we're going to talk about distribution so much in this, I'm going to start abbreviating it as dist. A distribution is symmetric. Why looking sad is symmetric if its left and right halves mirror each other. Each. Okay. So, and when that happens, we're going to have a picture kind of like this. So we're gonna have some axes. Oh, that's not straight at all. So let's try that again. Sure that they hold. No, okay. So here's our axes. We have a distribution, and then what we're gonna have here at this kind of peak of the data, the highest point, kind of imagine a value here. This happens when our mode equals our median equals our mean. And there we go. Okay, so symmetric distributions, the mode, mean, and median are all the same. And we're going to kind of imagine the left and right halves being perfectly mirrored. Okay. So then our next ones are going to be skewedness. Okay, I always want to make sure I'm getting this right. So if we're talking about skewness, all right. So a distribution is left skewed all right, if its values are more spread out on the left and what that looks like in a picture is if we have our axes, we have our graph, we have this tail on the left side. They're kind of spread out more here. So we're going to have still the peak of our data here is going to be the mode. And then it's going to be the median. Wait, so if we kind of imagine that we fill in the area under here, the median would cut it in half. I'm going to make it lower. And then the mean of our data is skewed to the left. So that's what we mean by skewed, is because of that outlier, it's pulling the mean left. Again, this is left skewed. And it has a tail on the left, is what I like to think of. Okay. So if we can have left skewed, that means we can also have right skewed. So what that means is I'm literally just going to take this data here. Oh, I didn't grab the L, but whatever. I was going to erase it anyways. Oh, it doesn't let me copy it. Ah, damn. Okay, let me undo all of that and just write it again. I was really hoping I could copy and not have to write everything because it's the same exact definition, but with the just right replaced. So a distribution is right skewed if its values are more spread on the right. Let me have these. Okay, there we go. There's right skewed. So same idea with the picture, except this time it's going to kind of have a hump here, and then it's going to have a tail over here. Looks like that wasn't very smooth. Let's try that one more time. It's up, and then it has a tail like that. It's close enough. Okay. So again, the highest point is where we have the most number of data points. That's our mode. All right, then the next one will be our median, which again is I'm going to kind of imagine is down here. median, and then our average will be next, which is our mean. There we go. All right, so this one has a tail on the right side, so our outliers are high. So this is right skew. It has a tail on the right. Cool. Okay. So if we wanted to talk about some word problems, so again, I'm going to jump back to the slideshow to show us the word pictures. Okay. So for each of the following situations, state whether you expect the distribution to be symmetric, left skewed, or right skewed. So the first one is heights of a sample of 100 women in the country. For B, it's the number of books read during the school year by fifth graders. And C, it's going to be the speeds of cars on a road where a visible patrol car is using radar to detect speeds. So basically, what's happening here in this third one, it's a little more confusing, I think, than the others, is there's a very visible cop on the road. And so some cars are going to really slam on their brakes and slow down. And most of the people will just kind of stay at their average. So if we talk about the solutions here, so for A, the distribution of heights of women is pretty symmetric. There's roughly an equal number of women who are shorter and taller. And so that the extremes are going to kind of cancel each other out. So for every woman that's only like 4'11", there's a woman that's going to be like 6'3". So they even each other out. And then the distribution of the number of books read is right skewed. So most fifth grade children read a moderate number of books during the year, but there's going to be a few readers that are reading far more than the other students. So there's going to kind of get skewed with the tail to the right. So a couple of kids are reading like 50 to 100 books in a year, where most of the kids are probably reading like 10 to 12. And then there's kind of a cap on the left side for the few kids that are reading like no books during the year. So it can't really get too skewed to the left because their middle is not going to be so big. And then for C, drivers usually slow down when they are aware of a patrol car looking for speeders, but a few drivers will be exceeding the speed limit, and then some drivers will slow to well below the speed limit. So the distribution is going to be left skewed with a mode near the speed limit. But we're going to have a lot of people that are anxious drivers that when they see a cop, they like slow down to 10 miles an hour. And so that's really going to skew us down, is those really cautious drivers that just slam on the brakes when they see a cop. Okay. So the next thing we're going to talk about is variation. So this is, I like to think of this as describing how skinny our graphs are. So if we have low variation, that means all of our data points are very, they don't vary very much. So they're going to be very skinny and all concentrated together. For moderate variation, we see that very like classic bell curve. We have a couple of values that are far below and far above, but most of them are right near the middle. And then we have high variation where we kind of have a very low fat graph. So things are spread. We have a lot of, just a lot of variation. Things vary greatly. So there's going to be a lot more spread out data. Okay. I think for these, just seeing the pictures is enough. All right. So for variation in marathon times, how would you expect the symmetry and variation to differ between the times in the Olympic marathon and times in the New York marathon? So I know you can already read the explanation here, but so Olympic marathon invites only the best of the best runners, the elite runners. So their times are going to be skewed pretty close to like the world record times. They're going to be very close together because it's the best marathon runners forever. Whereas the New York Marathon allows people of all abilities, so they're going to be very widespread. We'll probably have a couple people in the top, like almost outliers in the top of people who are like Olympic runners running in the New York Marathon, and we're also going to have people who walk the whole thing. That'll be at the very like left far side of the slowest times. So it's going to be pretty great variation. So for these two here, in the following situations, state which set of data you would expect to have less variation and why. So the first one is the weight of cars sold at a lot, which exclusively deals compact cars, versus the weights of cars sold at a general used car dealership. And then for B, the average number of miles driven by people in a small town versus by miles driven in a large city. All right. So for this first one, the first dealership deals with compact cars only. So compact small cars are already pretty small, so they should be weighing less. So I expect them to have a less variation because there's less variation in the kind of cars they're dealing with versus the weights of cars sold at a general used car dealership. They're going to have more variation because they're going to have things like a smart car and a huge pickup truck. So those weights of those cars are going to vary dramatically. So much wider spread of types of cars there. And then for B, the average number of miles driven by people in a small town, that's going to be a greater spread, I think, than miles driven in a large city because more people in a large city will take public transport, whereas in small towns, that's usually less available. So they're going to be needing to drive more. All right. So here's some solutions here. So the weight of compact cars should be expected to be closer together with less variation versus the general dealership. And then for B, the average number of miles driven by people in a small city. Oh, see, I think this is so wrong, but we're going to listen to them. So the average number of miles of people in a small town might be lower and less variation since people don't have to travel very far compared to the number of miles driven by people that live in a large city. I personally think that's wrong because I was imagining New York where like no one drives and everyone just takes the public transport. But the logic there is sound. In a small city, you don't have to go as far to get to the other side of town versus in a large city, if we're thinking like maybe Dallas, Fort Worth. In Dallas, to drive across all of Dallas and Fort Worth, that's a lot of driving you're going to have to do versus in Fayetteville, you don't have to drive near as far to go the same to the other side of town. So that's kind of the logic there. Okay. Okay. So this is where we're looking at skewedness using the students like the median mode and the low, yeah, the median, the mean, and the low and the high scores. So I know it's already showing the solution, but it's just easier than writing out all of these on the bad whiteboard app. So an exam for 100 students are given below. For the given exam results, briefly describe the shape and variation of the distribution. So the median is 85 and the mean is 71. So since our median is bigger than our mean, we're thinking we're going to be skewed left. Remember when I drew that picture? Wait, I can show you. I still have the picture up. Okay, so if we go back to the picture that we drew, we can see here that if our mean is to the left of our median, we're going to be left skewed. And if the mean is to the right of our median, we're going to be right skewed. So that's going to be when you're just given data, how you're able to tell that. Okay. So then going back to the PowerPoint. So since this one, the median is to the right of our mean, so our mean is to the left, we're going to be left skewed. And then our low score is a 9 and our high score is an 89. So that's a difference of 80. So that's, I think, pretty big variance. So looking at the solution, we're left skewed and high variation, so that's perfect. And this is the reasoning. The difference between the greatest and low score is 80, which is large compared to the number of students. Yeah, there's only 100 students. So that's where the high variation. And so the left skewed, again, that's where the mean is to the left of the median. And then for the next one, the exam results for 100 students is given below. So the median is 75, the mean is 75, and the low score is 60, and the high score is 90. So looking at this, we're going to have the median and mean are the same. So that means we're going to not be skewed. We're going to be symmetric. And then the difference between the highest and low score is 30, which is pretty small compared to the number of students where there's 100 students. So that means all 100 students scored within 30 points of each other. So pretty low variation. Again, this is normally where I ask for questions. If you have any questions on any of this in our these lectures that we're doing online, you can always email me about them. Okay. And so we're going to be looking at data where we're given graphs and we're talking about its variation in shape. So if we have this nice picture here, I'm going to do the best I can to imagine we kind of have okay. This one's really hard to do. Is there? No. Let me see if, now that it's the last thing we're doing, if I can write on this. Yeah, here we go. Okay. I don't know. Pick a nice blue. Wait, blue's already what we're dealing with. Let's go with a nice red. Okay, that must be pretty cute. So we're gonna kind of imagine, I know there's no tails here, but we're gonna imagine kind of coming up, having an arc, and coming down. I'm just using my mouse here, so it's not the best. If we really wanted to, we could maybe make it a little tighter where and maybe it would look something like this. Okay. So looking at this, we're going to have, if I can just type the, here we go. We have one peak right there around 90. And I think that this is pretty symmetric. There's no obvious skewedness to the left and right. Everything looks very symmetric. Okay, and the variation here, our highest score is 100 and our lowest score is 80. So that's going to be some low variation because the difference there is only 20 and it's for several football players. I mean, there's already 60 football players at 90 kilograms. So that's going to be low variation there for us. If it was using the whole 60 to 120, we would maybe say it had a higher variation. So that's just kind of looking at the graphs. They're going to give you a couple where you have to classify these different things. Okay, and so that's all on averages. And there's this nice thing here. I love our course coordinator adds a lot of these, like, I feel like they're Facebook memes onto the slideshows. I usually don't really show you guys those because they're not really adding much, but all right, let me get out of the slides. Just kind of stop sharing. Oh, I really hope that when I went to the slides, it actually worked. We're gonna hope that they did. All right. Well, thank you all for listening to this lecture. That's all that we're getting through today, and we'll move on to another section for our other snow day lecture. So you'll see me then. All right, goodbye.